Yeah, thank you. And thanks for organizing, by the way. I'm Aaron. I'm a PhD student at USC. And today I'll be talking about joint work with Brian Wilder, Bisha Dilkina, and Milan Tambe on training neural networks with downstream MIP solving in mind. So in practice, many of our AI applications involve optimization or MIP solving based off predictions of a machine learning model. So for example, in portfolio optimization, we train a model first to predict rates of return for individual assets. And then we find a return maximizing portfolio based off those predictions, which satisfies certain constraints, like limiting overexposure to a given sector using BGM constraints or limiting the number of transactions, etc. So our question in these types of settings is, how should we train the predictive model, that first stage, so that we optimize what we actually care about, the downstream performance or the solution of the MIP. And so the standard approach in this setting is to break the pipeline into individual components. So first we train the latest and greatest neural network to optimize a metric like cross entropy loss or mean squared error. And then using those predictions, we run our fancy MIP model to give us good decisions for the given predictions. So for instance, we use the predicted prices to give us a revenue maximizing portfolio. However, one big challenge for this setting is that the machine learning model is going to make mistakes. And especially in settings with low information content, this is a big problem. So to make matters worse, in this approach, the machine learning model has no idea how its mistakes will impact the quality of the downstream decision. So that's where decision-focused learning comes in. In essence, we want to automatically train the neural network for the single global objective of optimizing the downstream decisions. Whether it's the ROI of the selected portfolio, the number of successful housing matches, or the amount of energy saved by smart battery scheduling, overall our goal is to maximize the decision quality of the full pipeline. And in order to do that, we need to give the neural network information about how its predictions will impact the subsequent MIP solution quality. So the approach in our setting starts out in a very similar manner. We run the data through the predictive model to get predicted optimization inputs like those price forecasts from before. Then we solve the MIP with the predicted inputs to get a solution. We can then score the optimal solution based on historical data of how much value we would have gotten had we followed the suggested decisions. So for instance, we can solve the portfolio optimization MIP to get a portfolio, and then evaluate that solution on the next time period to get decision quality. Now, to update the model weights of the neural network, we need to compute gradients. And so the output layer gradients are easy to get as they ask us how changes in the solution would have impacted the overall solution quality. And so in portfolio optimization setting and in mixed integer programming, you can think of this as how changes in the portfolio would have affected the overall money we make, which is simply the individual rates of returns for the given stocks or the ground truth objective coefficients. The next step is the tricky part. We need to determine how predicted inputs to the MIP affect the overall optimal solution. And this is hard because of the discreteness and flexibility of the MIP, which makes it so nice for modeling, also makes it difficult to differentiate through. However, if we can get through that tricky step of differentiating through the MIP solution, then we can find the neural network gradients by standard backpropagation. And so here we just need to know how to update the model weights to move the predicted objective coefficients in the desired direction. So now let's try to tackle the hard problem of differentiating through the MIP component. And so one ray of hope is that previous work from Amos and Coulter in 2017 gave a framework for differentiating through quadratic programs. And more recent work by my collaborators has shown that this is possible for linear programs and submodular maximization. And so our contribution is to bring decision-focused learning to the broad class of NP-hard problems captured by mixed integer linear programs. And so overall, we're working with one true north in mind, that is optimizing the downstream decision quality of the neural networks. So our approach will be to consider the MIP as a layer in a network, MIPaaL. In particular, MIPaaL, the MIP layer, will take as input objective coefficients predicted from earlier network layers, as well as fixed instance parameters, and it will output the optimal solution given by those predicted objective coefficients. For instance, in portfolio optimization, it will take as input predicted prices, diversity constraints, and budget limits, and it will output the chosen optimal portfolio for the given predicted prices. Here's just some notation for writing out the optimal MIP solution that we'll use later. And overall, we'll evaluate the loss by using the ground truth objective coefficients multiplied by the optimal solution X star. So now, of course, back to the challenging part. We need to differentiate through this layer in order to use it for backpropagation. We need these tricky gradients. And so our proposed approach is to solve a tightened continuous relaxation of the MIP with a pure cutting plane approach to preserve the integer solutions and to avoid breaking the solution space into multiple components. And thinking back to our intro to optimization class and the password to this Zoom meeting, we can relax the problem and then add cuts to tighten the formulation while leaving the integer points feasible with approaches like Gomery cuts or any of these other amazing tools we just saw. So what we're left with is a continuous linear program with potentially exponentially many constraints whose optimal solution is representative of the integer optimal solution. And so once we have a tightened LP, we can differentiate the output of the convex linear program with respect to the objective coefficients by differentiating through the KKT optimality conditions as was shown for linear programming in previous work. The idea here overall is that by adding a small quadratic regularization, we can implicitly define the unique optimal solution as a function of the predicted objective coefficients. So now we'll evaluate our learning approach in several settings. Note that actually at test time, we can use any solver we want, whether it's branch and bound or any other method. And so we'll evaluate on 3 domains. The first is portfolio optimization, where we predict rates of returns from historical data and want to maximize the amount of money we make, subject to constraints on sector overexposure, transaction limits, and individual asset exposure. And we evaluate on both US and German historical stock data. We also evaluate on energy-based knapsack problems, which consider scheduling battery discharge, where we predict energy prices and try to maximize our total revenue with weighted budget on when we can sell. And here we'll use real-world energy price data from the ICON Energy Scheduling Challenge provided by Amir Demirovich, who was very kind to provide that data. And lastly, we'll evaluate on a variant of bipartite matching where we add lower bound constraints on the % of interdisciplinary and intradisciplinary matches. And we run our models on the Cora citation network data to make decisions for a citation recommendation engine, maximizing the number of successful matches. So here are the testing results using different training methodologies in each of our setups. In blue is a model performance of MIPaaL's MIP-based loss. Orange is trained using just the root LP relaxation and not generating cuts. And green is the standard 2-stage approach, which is trained ambivalent towards those downstream decisions. In these settings, higher is better in that we want our portfolios to have high ROI, provide matchings with high success rates, and find battery schedules to maximize the prices we can sell at. Oh, yeah, and so the main takeaways here are that training neural networks for the correct loss function yields much better decision quality at test time. And additionally, if we use just a simple LP relaxation without adding cutting planes, the overall decision quality suffers and often can't be the standard 2-stage approach. And taking a look at machine learning performance, we can actually see that the machine learning loss functions we were trying to minimize are not necessarily aligned with the downstream decision quality. So we can see here that actually the 2-stage approach in green is best across the board, but didn't come close to the MIP-based layers in decision quality. And lastly, we evaluate on how well our model generalizes. So to do this, we train a model to pick among 30 US stocks and then test that model on problems with the same size but different data. So first we evaluate on picking from a set of 30 US stocks, and second, we ask the model to pick among 30 German stocks here. And again, MIPaaL in blue outperforms baseline methods which are trained to optimize those machine learning metrics. Additionally, we're going to evaluate model performance when scaling up model sizes. So here we're still training a model to pick among 30 stocks, and we're evaluating how well it picks among 50, 100, 200, and finally the full S&P 500. So in blue, orange, and gray are the transfer learning approaches. And interestingly, as we can see on the right here, the model trained to optimize over 30 stocks outperforms baseline approaches that are trained to pick between the full 500 stock data set. So this indicates the model is learning something general and transferable about which stocks to put in the portfolio and which to avoid. So overall, we find that using optimization-based layers gives better decision quality, and using the right model is important for end-to-end training. But most importantly, when you're using machine learning to inform decision-making, you should train the model with the downstream decisions in mind. Thank you, and let's discuss any ideas on Slack.